Here is the first order linear differential equation. Dy dx is equal to 2xy minus x. It's not, to be sure, in the standard form of a first order linear differential equation, but we can modify it so that it is. And recall that the first order linear differential equation in the standard form is dy dx plus p of x y is equal to q of x. And one technique to solve such an equation is to use a so-called integrating factor. In this case, as we've shown in another video, we can prove that it is mu is equal to e raised to the power of the indefinite integral p of x dx. So let's look at this equation and rewrite it, so to speak. We can get dy dx minus 2xy is equal to minus x. Now clearly, p of x is minus 2x. So we can think about that integrating factor, mu, is equal to e raised to the indefinite integral minus 2x dx. So now we have e minus 2 over 2x squared. And that's just e to the minus x squared. All right. So we can take this integrating factor and multiply the entire equation by that. I like doing that because that explicitly, so to speak, shows what we're doing to that equation. It shows why this technique works. So we have this here. We'll multiply it by our integrating factor. So now we have e to the power of minus x squared dy dx minus 2xy e to the minus x squared power is equal to minus x e to the minus x squared power. And now this left-hand side, because the whole point of that integrating factor is that that expression is equivalent to the derivative of the product e to the minus x squared power times y. And now we can anti-differentiate. And also, by the way, of course, because this expression here and this expression here are equivalent, we can also test that, of course, and to make sure that they are indeed equivalent. All right, so let's just anti-differentiate both sides of the equation. The right-hand side is also with respect to x. So we know the fundamental theorem of calculus. The left-hand side is just e raised to the minus x squared power y. But what about this right-hand side? It's not exactly clear what this is, but it seems we can do a u substitution. So let's think about that for a little bit. So we can say that u is equal to minus x squared, which is great because obviously we have this x here, we have this minus here, so that's definitely going to be handy. Du, the derivative, is equal to minus 2x dx. So right now, you can think of it this way: we have minus x e to the u dx. So we have this minus x, we have this dx. We need a 2, but we don't want to radically alter our expression, so we'll have to multiply it by 1/2. And now we have one-half e to the u du, which is 1/2 e to the u, and that is e to the minus x squared. So that's pretty easy, actually. So let's put this stuff together. So we have e to the minus x squared power y is equal to 1/2 e to the minus x squared power, and then we'll add our arbitrary constant. We want to solve for y. So let's just divide everything by e to the minus x squared power, e to the minus x squared power, e to the minus x squared power. So we have y is equal to 1/2 plus, well, this is a negative exponent, so we can, so to speak, bring it upstairs. We bring it to the numerator. So we have c times e to the x squared power. And this is our final answer.